Transporting the locomotive, the tender, a truck and the battery, plus various pieces of test gear out to my test track in the garden will be a significant logistical exercise. There's also the possibility of getting everything out there only to find some problem that can't easily be fixed on site. I've tested most parts individually, but not together, so I've decided to carry out as much combined testing as possible before transportation. Early on in the project I'd built 5 rolling road units for the loco, but had not used them, so as they were available I decided to use 3 of them for testing the tender. The tender has been run previously on the test track, but that was with an earlier control board. Firstly, I fitted some Teflon tape to the bottom of the units and polished the bench top with some silicone polish, so that I was able to slide the assembly around easily. This clip shows the tender being powered from a stabilized power supply set to 12 volts and controlled from the hand controller. The control card is temporarily mounted in a readily accessible position. The first test showed a problem. Although the motors worked as required, the speed readout on the cycle computer was jittery and stopped altogether above 2 km per hour. The encoder once per rev pulse links through the control card where there is a test point, so I was able to monitor it with an oscilloscope. The encoder specification says that this pulse is 90 degrees. I took this to mean a quarter of shaft rotation. However, the oscilloscope revealed that its width is actually a quarter of the period between the successive pulses of the 1000 pulse main output of the encoder. A simple calculation showed that at 1 km an hour, the pulse was actually 50 microseconds wide, not 50 milliseconds as I'd expected. This was far too narrow to operate the cycle computer correctly. There were 2 possible solutions. I could use the pulse to trigger a monostable, so the output pulse would be set to a fixed suitable width. Or I could use a divider. The second approach was simpler, so I decided on that. This diagram shows the idea. It uses a CMOS CD4013B dual D-type, so that divide by 2 or divide by 4 are available. I decided to divide by 4, which at 1 km an hour gives an update every 800 milliseconds, with a pulse width of 400 milliseconds, and at 10 km an hour an update every 80 milliseconds with a pulse width of 40 milliseconds. This arrangement gave stable speed readings. This diagram shows the control board with the 4013B added at the top right, conveniently close to the Traco DC to DC converter that supplies the 5 volts for the encoder. This seems a suitable time to show the circuit of the control board again. This diagram shows the position of the test points identified on the circuit diagram. This diagram shows the position of the links that can be removed during testing. The locomotive is on a bench the other side of the room, and it's not possible to get the 2 units close together. I therefore decided to initially test the loco drive by coupling it to a Fasco 250 watt motor, the same as the loco motor, sitting on the test unit that was used earlier. However, there was a supply problem. My stabilized power supply could only provide up to 5 amps, and that was inadequate for both units. I could have used a battery, but since I only had one available, I wanted to conserve that for tests on the track. I started to search eBay for a higher current supply, but by chance came across 12 volt computer server power supplies. These are available second hand in good condition for amazingly low prices. A 460 watt 38.3 amp supply could be bought for only £7.95 delivered. Others are available up to 100 amps and are mostly bought by people setting up crypto mining stations. I decided on the 460 watt version. It was designed by Hewlett Packard, is very compact, and has an excellent performance with much lower electrical noise than the Chinese LED supplies on eBay. The supplies are not short-circuit proof, so I wired a 30 amp car fuse in my test lead. This diagram shows the pin connections to the edge connector at the rear. When the mains power is applied, the unit is on standby until pins 33 and 36 are shorted together. I fitted a switch to do this. The 0 volt and 12 volt areas are repeated on the underside of the edge connector, so I linked them together to load share. Pin 37 provides a separate 12 volt 2.5 amp supply, which is always on when the mains power is supplied. I used that to power the small panel meter. These photos show how I fitted an output panel with a small voltmeter inclined towards the front. The second switch enables the meter to read voltage or current. I provided bolted and 4mm output connections. At the front is a socket for an IEC connector and a latch lever that originally prevented the power supply from being removed from its cabinet without removing the mains plug. I found this arrangement rather inconvenient, so cut off the lever with a Dremel and bought a right angle IEC plug. It was easy to remove the plug cable clamp and drill the back to reposition the ferrule. I blocked off the original ferrule hole, and since there was now no cable clamp, glued the cable securely in place with Evo stick. Finally, I fitted a switched mains plug so that the unit could be turned off without unplugging it. This clip shows the speed measurement performing properly. It also shows the 250 watt Fasco motor being driven at the same time as the tender. With the tender at 3 km an hour, the Fasco is doing 1140 RPM. Taking into account the local gear ratio and the local wheel diameter, this is equivalent to the local being 17% faster than the tender. However, neither unit was under load, so it doesn't mean much, and anyway the speed settings will have to be trimmed on the track. The voltage and current readings on the hand controller seem to be working okay, so this is as far as I can go at present. The next step will be to make up a long interconnecting cable between the tender and the loco on the other side of the room, and block the loco up off the ground. I will then be able to test the tender and loco together, and try out the sound system via the loco wiring, and try the chuff system working from the synchronizer disc. That will be covered in Part 6b. Part 6c should be the final testing on the garden track.